Okay, so the Bragg formalism gives us a relationship between the scattering angle, okay, sine theta, the lattice spacing, that is the distance between atoms in the crystal, okay, along some Bragg plane series of Bragg planes, and the wavelength of the radiation, which for which you would see a um, interfere for which you would see constructive interference at that angle. Okay, and so what we want to do now is we want to calculate um, the wavelength that would correspond to a particular Bragg spacing, a particular value of d, spacing between the Bragg planes in for nickel. Okay, and which actually was known at the time from X-ray scattering experiments, which is again how where the Bragg scattering formalism actually arose. Okay, and so we want to compare the wavelengths which are predicted by the Davis and Germer experiment, and then see whether that wavelength is agrees with the prediction of de Broglie for the energies, the kinetic energies in the Davis and Germer experiment. Okay, so just in order to do that, one thing that we have to do is we have to compare the angle theta, which we've used to develop the Bragg scattering formula, okay, and the scattering angle which Davis and Germer measured. So if we call this scattering angle phi here, okay, then that's the angle between the incoming beam and the outgoing beam, and so that's this angle. Okay, that's phi. And so what we see actually is that phi, this is phi, sorry, went away when I switched slides, and this is phi again. So what we see is that phi plus 2 theta is equal to 180 degrees. Okay, so phi plus 2 theta is equal to 180 degrees as given by this geometry. Okay, and so theta is equal to 180 minus phi divided by 2. So for phi equals 50 degrees, which is the scattering angle that Davison and Germer observed this peak in the intensity, in the electron scattering intensity, that corresponds to theta equals 65 if you just use this formula. Okay. Now, for nickel, again, X-ray scattering experiments. So Bragg scattering with X-rays had already shown that the spacing between Bragg planes again was equal to 0.091 nanometers. Okay, and so we already had that number, so we can plug it in. So 2 times d, okay, d times sine of theta, and again theta is 65. If we compute this, we get that is equal to 0.165 nanometers or 1.65 angstroms. So the question is that equal to some multiple of the wavelength that we would predict from de Broglie? Okay. Well, what does de Broglie say? Again, let me remind you, in the de Broglie experiment, we have, the de Broglie hypothesis, we have for this experiment, again, the electrons accelerated through 54 volts potential, and so they have energy of 54 kinetic energy of 54 electron volts. Okay, and so if we use the modified de Broglie hypothesis that we wrote down a few slides ago, we have that the wavelength is equal to 1240 electron volts times nanometers divided by this quantity, and when we plug all that in, we get something which is 1.67 angstroms, which you can see is very, very close to what Davison and Germer predicted.